The second method we are going to talk about, the bracketing methods, is false position method. And the bisection method we saw earlier is perfectly valid and actually very robust, but it's a brute force approach and it's really inefficient because it is not easy to find the root as accurate as possible. You need many iterations. And the reason of it is that in dividing the interval from xl to xu, lower and upper bounds, into equal halves, because we are having the midpoint, no account is taken of the magnitudes of fxl and fxu. So we don't use really the function values. We just use xl and xu and continue from there. And it takes time in terms of iterations to find the root. For example, here you can see a function, which is the blue line. And this is the actual root actually over here. And if xl is much closer to 0 than fxu, so what we mean is that we choose an xl and xu values initially, and we checked the function values as well. The function values are on the y-axis. Which function we question which function is closer to the 0. So you can see xl function value is closer to the 0 compared to the fxu value. Then we say that okay, then the root should be closer to fxl or xl, because fxl is closer to the 0. If we go a little bit further, we will have the root of the equation over here. So the alternative here, the false position, says if we draw a straight line from fxl to fxu, as you can see here with the black line, we can simply have the intersection with the x-axis, which is xr, as the solution, the approximation for the root, which makes this function 0. And this intersection of the line with the x-axis represents an improved estimate, and replacement of the curve by a straight line gives a false position of the root. So this straight line is a false position of this function actually. And that's why it's called method of false position, or in Latin it's called regula falsi. It's also called linear interpolation method because we have kind of a linear interpolation between the xl and xu to get the xr. So this is actually a good way of predicting the root function much quicker than the bisection method, because we use also the function values. So we are going to see the false position formula in the slide. If you remember, in the bisection method, we only have finding the midpoint by dividing xl and xu by 2. But over here, now we are going to have a linear interpolation. That's why we will have two triangles, as you can see. One is at the bottom here for the xl, and one is for the xu, between xr and xu. So the similarity here shows that the fxl, the y-axis here, over here, divided by xr minus xl, this one, the horizontal, will be equivalent in ratio to the fxu y-axis of this and x-axis of this, xr and xu. So this formulation gives us the actual formula for the false position. Let's see how it works. Let me write on the right hand side that we can actually simply have a cross product of this and have it here. So what happens is f xl and xr minus xu is equivalent to f xu xr minus xl. So this is the equation. Now we are going to rearrange this. What we can do is simply we can isolate xr, because we want to find that. If we isolate xr, you can see from here we have fxl, and over here we have fxu times fxr. So if we move this to the left side, it will be minus fxu. The rest will be on the other side. Then I will say equal to, the rest is actually fxu and fxi. sorry, xun fxl, and over here fxl and fxu, xl and fxu. Let's divide this by this value here, because we want to isolate xr. So if we divide by this, fxl minus fxu, to both sides, fxl minus fxu, these will cancel out, then xr is equivalent to xu fxl minus xl fxu divided by fxl minus fxu. So this is the formulation for finding the root or estimating the root, let's say, in the false position method. Instead of the midpoint, we are using this. And to compare, actually, I'm writing xr for bisection. Bisection, let's say, xl plus xu divided by 2. So you can compare these easily. You can see that we have the function values as well. We can a little bit further simplify this. And I'm not going to give you the details of the simplification, but you can check your book if you want to. I will just write the result. Simplifying. Basically, we will use some operations to have less calculations. Then xr is equivalent to xu minus fxu xl minus xu divided by fxl minus fxu. The denominator, the below part, is the same, actually, you can see, but at the top we will simply have xu as one single term by having this term over here as well. So this is the final formulation that we will use to find xr value for the false position formula. Let's check in this slide the steps of the false position method. So the xr value is estimated by false position formula using the formula that we showed earlier, this one. And then we replace whichever of the two initial guesses, xl and xu, or xu, yields a function value with the same sign. So we check this sign calculation again, as you can see here. So this is simply very similar to the bisection algorithm. The only difference from the bisection algorithm is that instead of using midpoint approximation, we use the new false position approximation, as you can see here. The other steps are the same. So if the multiplication is below 0 with the fxl and fxr, we set xu equals xr. If the multiplication is greater than 0, then we set xl equals xr and continue to the second step and calculate this again and repeat this process until either this fxl times fxr equals 0 or a convergence criteria or a stopping criteria is achieved.